Hello, Chem students. This should be our last slide presentation on Chapter 1. It covers 2D and 3D structures. These are important structures for you to be able to draw. So there's a set of rules, and I'll read through the rules, but we're actually going to work several of the examples in the coming slides. So you might not retain everything, but we'll go through all these rules several times. First, you want to sum all the valence electrons from the atoms in a formula. Okay. You want to draw a sigma skeleton from the condensed line formula. This could be challenging a little bit, so you have to have a little experience here. Each sigma bond counts for 2 electrons. All the rest of the electrons will be added in, and they will become either lone pairs or pi bonds. When you add in the extra electrons, you want to use the most electronegative atoms first. So if you had a fluorine, you would add them to the fluorine over the oxygen, oxygen over the nitrogen, and nitrogen over the carbon. And if there's some left for several carbons, you can kind of spread them out since electrons repel each other. Now, if you come up with some atoms that don't have a full octet, and there's a neighbor that has a lone pair, then you can borrow those. And if you have more than one neighbor that has a lone pair, then you can borrow them more than one way, and those will become resonance structures. So resonance is a real central idea in organic chemistry, and this particular topic will show that several times. So remember, an atom's hybridization is determined by the resonance structure where it has the most bonds. Where it has the most bonds, you'll be able to best see how many pi bonds are present. Now this could be kind of hard because this means you have to draw the resonance structures to be able to do that. And you might overlook a resonance structure, and if that was the case, then you might not be able to recognize the hybridization of a particular atom. So this is kind of an important idea, but it does require some experience and some practice. Now when you draw resonance structures, we have specific arrows that are used in specific ways. The double-headed arrow, like you see here, is drawn between 2 resonance structures to show that they are related by resonance. Okay? If you move electrons, if you move 2 electrons at once, then you'll use a full-headed arrow. You start where the electrons are at the beginning, and then in the next structure you point to where they will go in the next structure. If you only move 1 electron at a time, which we won't do, that'll be in Chapter 10 that we see that. We'll just use a half-headed arrow. But for right now, we'll only be using full-headed arrows. So our goals as we write these resonance structures to get to the best resonance structure is we want to maximize the number of bonds and full octets. That's the number 1 goal. Okay, now if you've done that, then you want to minimize any formal charge that's present. So sometimes you can have the same number of bonds and full octets, but you have one structure with formal charge and one structure without formal charge. So without formal charge is better, where you don't separate the charge. And third, you want to keep the formal charge consistent with electronegativity. So if there was a carbon and a nitrogen, you would rather the carbon be positive than the nitrogen if all the other rules are in effect. But that's not always the case. So sometimes the electronegativity is inconsistent with the charge that you have because these other rules have taken precedent over that. Now, to translate that 2-dimensional structure into a 3-dimensional structure, our first guideline will be draw a 2D structure. So that's a challenge. That's not like a simple little thing you're going to do. And if you draw all the resonance structures and everything, then you'll be able to figure out what is the hybridization of all the different atoms, which means you'll know the shape, and you'll know the bond angles, and you'll know the number of sigma bonds and pi bonds and any lone pairs. So this is a real important part to getting to that 3D structure. Okay. Now if you've drawn all the resonance structures, you'll be able to look up and down and find a particular one where a particular atom has more bonds. And that's where you will decide the hybridization of that particular atom. And that'll be different for different atoms and different structures. So you really have to draw all the resonance structures to see every possibility. Okay? So remember, the hybridization of any atom is determined by the resonance structure in which that atom has the maximum number of bonds. Okay? Real important idea. So I say here, if I make a big deal about it, Maybe you won't forget it, but you probably will. Almost all of us do that, certainly at the start when you're learning. Now, as far as drawing the 3D structure, you want to try to draw it as much as you can in the plane of the paper, or if you're working on a board, on the board, because that'll make it a little easier. And so the thing that helps the most, I think, is to start off, if there's a triple bond, to put that into the plane, because all those atoms in that straight line will be in a plane. You don't have to try and draw that coming out in front or going back behind the plane. Aromatic rings, they're also good to draw in the plane. Okay, the SP2 guys are very flexible, so you can draw them coming out of the plane, going back of the plane, as we'll see. And then the SP3, if you have a whole chain of those, you want those to be kind of in a linear line in the plane of the paper. So these, we've all seen these before in another presentation, so I'm not going to go through real quick, but these are all triple bonds. We have carbon sp hybridized, we have nitrogen sp hybridized, we have oxygen sp hybridized. So these are all linear shapes that we're talking about. And so remember I have the pi bond drawn with the p orbitals as simple lines and then a line connecting them. So we have on top and bottom one single pi bond. And then we also have in front and back one single pi bond. And you'll notice that the front is heavy lines and the back is dash lines, okay, to indicate the 3 dimensions. And in this particular arrangement that I have here, we're kind of looking at these from the right side, all right? So I don't know how much you can see the perspective and so forth, but this is sort of an important idea because you don't want to draw partly from viewing on the right and partly from viewing on the left. It just wouldn't make sense. Okay, so let's take a look at a view from the other side. So if we viewed from the left, notice how everything kind of swings over to the other side because that's your perspective that you're looking at here. So I don't really care which way you do it, just as long as you're consistent with the rest of your structure. Okay, now for the double bonds, remember we have many ways of doing this for sp2 atoms. And so they can be carbon, they can be nitrogen, they can be oxygen, they can even be fluorine if we have a positive formal charge, because fluorine would normally only have one bond. So if we make a double bond, then it has to have a positive formal charge. Now looking at it side on is pretty easy. So this is a good way to start if this is all you have, but if you have a triple bond, you might want to put that into the plane first. Because the thing is with double bonds, we can have them going back, we can have them coming out, we can have them coming out, we can have them going back, and you can sort of tell which atom is drawn first by what you put in between the two carbons. So since this is a dash, it must mean that I drew this carbon first and put a dash back. On the other hand, if I had drawn this carbon first, I would have a wedge coming out. And so you can see that could go either way. And so this is an ambiguous bond in the middle. The other bonds are not ambiguous. This has to be a dash. This has to be a wedge. And you'll notice there's a lot of parallel bonds here. And if you recognize that, it makes it easier to draw the structure more accurately. Okay, so these two are parallel to each other. One's pointing to the right and one's pointing to the left. Okay, and then a dash and a wedge on either side. Now sometimes I just write a simple line here because it is ambiguous. I don't really care about this line so much. But the dash and the wedge have to be drawn correctly to give it the right perspective. And you can see over here, I drew this one on the left first because it's a wedge coming out. And you'll see the lines pointing to the left here in the back. That's not the case. Over here, the lines pointing to the left in the front. And so just to show you, there's many different perspectives for the pi bonds. Okay, and so I must have drawn this one first because it's a dash, or maybe I didn't even draw either one as a dash or a wedge. I just put a simple line. Okay, and then don't forget the 2 electrons in the pi bonds. Okay, I want you to draw those because we'll be using those to do reactions later on. Now, as far as the sp3 guys, if you have more than one, generally it's good to draw them in sort of a zigzag shape. There's so many ways you could draw these because they could be coming out, they could be going back, and when you start to do that, you have to be a really good artist to be able to do that. So the easiest way is just to take this, say I have all these guys in a row here, is just to follow the lines up and down. Okay, so I go down, up, down, up, down, up. That's my chain right there. And then off of each of these carbon, oxygen, nitrogen atoms, there's going to be a dash and a wedge. Okay? And so again, there's this matter of perspective. If I'm looking at it from the right, then my dashes and wedge will look like this. So if I get the first one in correctly, so here I have a wedge coming out and a dash going back. This is sort of on your left side if you were looking at it, sort of your left hand, and this is sort of be your right hand. But once you do this, then all the rest of them will be the same down the line. They'll all be parallel to that. And so this guy right here, notice I have on the left side a wedge. That's sort of where my left hand would be if I could reach out and touch it, or this would be the right hand, a dash going back. And once you do this correctly, it would be the same all the way down the line. Now, if you instead, in your mind, if you had looked at it from the left side, then it would be a little bit differently. So then you would come over here, and the dash would be on the left, the wedge would be on the right, the dash would be on the left, the wedge would be on the right, and whatever you do on the bottom, it would be the same all the way down, and whatever you do on the top, it'll be the same all the way down. Okay, so we've drawn those before. I just wanted to remind you of the 3D structures, the 3D features that are there. So now I have several structures. We're going to go through and work the problems out, but I would suggest that if you pause the slide, see if you can sketch it out and make your own structure, and then check and see if it's correct. Now when I give you a condensed line formula like this, I'm telling you the connection of the atoms, and so you have to see that the two hydrogens here are on the nitrogen. And then it looks like the carbon is attached to the H and the F, and then it looks like there's a CH2 attached to the two hydrogens on the carbon, and then there's an O, and then there's an H. Okay, so there's actually several functional groups in here, which we will study. Okay, let's take a look. And so what we see is, yeah, the two H's are on the end. The carbon has the H and the F. This has a CH2 and the O and the H. Now, we want to fill in all of the electrons that go with these atoms. So I have two carbons here. They're going to contribute 8. I have one oxygen, contributes 6. One nitrogen contributes 5. One fluorine contributes 7. I have 6 hydrogens that contribute 1 each for 6. Add that up, it comes out to 32. So remember, every sigma bond is 2 electrons. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's going to be 20 electrons that are in sigma bonds, but we have 32. So there's 12 extra electrons that are left over, and we have to add those on. And the way I suggest you do that is go to the most electronegative atom first and fill up its amount of electrons. And then you can go to the next most electronegative atom and add in until you run out. If you don't run out and you still have electrons and there's carbons, then you start adding them to the carbons. So in this case, we go to the fluorine first. Remember, we have 12 left over. I put in 2, 4, 6, and now the fluorine is full. I have a full octet. Then I go to the oxygen. I need 4 here, so I add in 2 more, so that's 10. And then I go to the nitrogen. I add in 2 more, and I ran out of electrons. And now everybody has an octet. This is a nice simple structure. You'll notice there's no pi bonds. Okay. Now I'm doing this very methodically, adding in all these electrons. But in fact, if you had a little bit of experience and familiarity, you could just look at this structure right here and see, I need 3 lone pairs on the fluorine. I need 2 lone pairs on the oxygen. I need 1 lone pair on the nitrogen. And so you could use just sort of intuition for filling that in. But when you're starting out, you don't necessarily have good intuition. So this is a mechanical way of doing that. Okay, let's take a look at another one. So in this one, it looks like we have an F and an H connected to the carbon. Now you might think, oh, the F's connected to the H and the H is connected to the carbon, but that can't be, because hydrogen only makes 1 bond. So this is where drawing the 2D structure could be a little bit confusing if you don't really know exactly what you're doing. So practice will make you more familiar. You'll know that hydrogen only has 1 bond. And then I have that connected to a carbon. So it looks like there's only 3 atoms connected to this carbon. We're going to need a little bit extra. We'll see in a minute. Then that carbon looks like it's connected to an H, and then the carbon's connected to a carbon. Notice I can't write them both next to the carbon, so I put the H in the middle so I can see that the carbon is on this H, and then this carbon is next on that carbon. And then there's another carbon that has an O. Now this is a real tricky one, because it looks like it would be C bond to O, O bond to N, but that's not going to be possible, because then this carbon would only have 2 bonds. So whenever you see an arrangement like this, you want to suspect that there might be a carbon-oxygen double bond. and then this is continued on the other side of that. Okay, so give it a try, see if you can do that, and then we'll take a look. Okay, so here's the F and the H on this carbon. Then this carbon has the H, and then this carbon is attached to a carbon and a carbon, and then an O, and then an N and two H's. So in fact, I kind of tricked myself on this one because these two carbons right here are actually a triple bond. But let's see if we can figure that out. We have 4 carbons, that's 16 electrons. I have 1 nitrogen, that's 5. 1 oxygen, that's 6. 1 fluorine, that's 7. 4, 1, 2, 3, 4 hydrogens, that's 4. That totals up to 38. Okay, so if I count the sigma bonds, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, looks like there's 20 electrons in sigma bonds, so there's 18 electrons left over. Okay, well, we know where they're going to go first. We're first going to put them on the fluorine. So that's 6 of our 18. Then we come down, we'll put 4 of them on the oxygen, so that's 10 of them. We'll put 2 of them on the nitrogen, that's 12, but I still have 6 electrons left over. And if I look at the carbons, they're not completely full. Okay, this only has 6 electrons, this only has 6, this only has 4, and this only has 4 when I'm looking over here. So what I'm going to do is I'm going to add 2 to this carbon and 2 to this carbon because they look the most bare of electrons. They need the most. And then I'm going to put 2 over here, far away as I can get from that because of electron repulsion. And so I'm going to put them in here. Now I still come out that this guy needs some electrons. So I'm going to borrow them from this side because that completes these 2 as a double bond. No formal charge. And then these guys I'm going to borrow 2 in this direction and 2 in this direction, and that'll give me a triple bond right here. And so now I have no formal charge. This looks to be a very good structure. Okay. Now when I was here, I could have borrowed from this side, but that would have forced me to leave these electrons on this carbon and draw a minus formal charge. So that is a contributor, but that's not going to be nearly as good as not having any formal charge. Okay, so that's a little bit tricky on this one because this is an unusual group that we're looking at. Okay, here's another one. So I have an O and then an H and then a C. So now I know pretty much for sure that this H is attached to the carbon and the O is attached to the carbon because the H cannot be in between them because it only makes one bond. And then I have a CH and an OH. So these 2 look to be on this carbon in the middle. And then I come down to a COOH. So there's a lot of wrong ways of drawing this. You might draw carbon, then oxygen, then oxygen, then hydrogen. But then you would have a problem because the carbon couldn't be filled in with 2 bonds. So instead, when I come to this, I'm going to draw a carbon and then 1 oxygen off to the side, and then a carbon, the same carbon, with an OH. Alright, so this is something you'll have to learn to recognize. This is going to be a carboxylic acid. Okay, so let's take a look. So we make our sigma connection. We tie all the atoms together. So I have a CH and an O. Then I come to a C that has an H and an OH. Then I come to a C, and notice how I put this oxygen off to the side, and then this as an OH on the other side. Okay, if I tried to put them both on this carbon as double bond O's, that wouldn't work. And then put the H here, that's just not going to work. And if I put OOH, I'm not going to have any electrons to fill in this carbon. That's not going to work either. So this is a very common pattern. C double bond O. It's about half of organic chemistry. So now if we count them all up, 3 carbons, 12 electrons, 4 oxygens, 4 times 6 is 24, 4 hydrogens. That adds up to 40. Sigma electrons are 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So again, we got 20 sigma electrons. There's 20 left over. So I don't see any fluorines, so I'm going to start to add those to the oxygens. So I add 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I used up all my electrons by adding them to the oxygens. Now we'll see if everything looks good. Oops, this carbon is missing 2 electrons, so I'm going to go to the neighbor that has a lone pair and bring those in and make another bond here. So that's going to be a carbon-oxygen double bond. And if I look here, I could borrow from the top oxygen to make a double bond up there, or I could borrow from the bottom oxygen down here to make a double bond here. This guy doesn't need any electrons. And so what you'll see on these two structures, these are called resonance structures. This one looks good. There's no formal charge. Okay. This one, I have 3 bonds on oxygen, so that would have a plus charge. And I have 1 bond and 3 lone pairs, that would have a minus charge. So this is not as good as the structure to the right up here, but it's not bad. Okay, this is still a contributor that we have to be aware of. All right. That would also tell us that this oxygen right here is sp2 hybridized. Notice how it has a pi bond. I don't see that up here. So when I look at this, I'm thinking this is sp3. So this is a case where you have to draw the resonance structures to recognize the hybridization of the atoms that are there. And if I look down here, I would say, oh, this doesn't have a pi bond. It must be sp3. Okay, but what I'm not seeing is that it does have a pi bond. If I draw this resonance structure, I can see it. So again, go to the resonance structure where an atom has the most bonds. This oxygen has the most bonds here, so I'll decide what the hybridization is here. This oxygen has the most bonds here, so I'll decide what the hybridization is for this guy here. And in this case, both of them would come out sp2. Okay, so here's another one. Now this one, I have a whole bunch of carbons together, and so I tell you there's a 6-carbon ring. So we'd have to make a ring for that. And then this is off to the side of the ring, must be carbon connected to nitrogen, and that's connected to the ring. So that's a little tricky. It's actually an aromatic ring. Let's take a look. So the initial connection would look like this. Here's our 6-carbon ring. I have a hydrogen on each carbon except for the carbon that has the carbon nitrogen. Okay, I have 7 carbons, that's 28 electrons, 5 hydrogens, that's 5, 1 nitrogen, that's 5. Totals up to 38 electrons. I actually have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I have 26 electrons and sigma bonds. That leaves 12 electrons left over. So now I go to the nitrogen first and I fill those in, 2, 4, 6. I still got 12. Now I'm going to alternate the electrons around the ring. I can see every single carbon needs more electrons, but I don't want to put them all together because electrons repel each other. So I put 2 here, 2 here, 2 here, and then I'm going to use those electrons to fill into the neighbor to give it a pi bond. Okay, so I have a pi bond here, and a pi bond here, and a pi bond here. Now I could have gone the other way. I could have put the pi bond here, and here, and here, and that would be a different resonance structure, which we're not showing in this particular example. This carbon here needs 4 electrons, and so if I go to the nitrogen, I could borrow 2, and then I could borrow 2, and that would make everybody pretty happy. The carbon has 4 bonds, the nitrogen has 3 bonds and a lone pair. Notice there's a second and third bond, so the nitrogen is sp hybridized and the carbon is sp hybridized, and all of these carbons are sp2 hybridized, so we could go ahead and try and draw a 3-dimensional structure if we had drawn this structure. Okay? So here's another one. We're actually going to draw 3-dimensional structures now. So I would have to connect, I got 3 hydrogens on the carbon, and then I got a CH and a CH, so it looks like probably there's going to be a double bond here. And then I have a C and a C, no other atoms. This looks like it might be a triple bond. Then I have that funny pattern where I have 2 oxygens on this carbon. Probably both of them are attached to the carbon, and then one of them has an H. So let's try and draw the sigma framework. So here's the sigma framework, CH3, CH, CH, CC, CO, and COH. Okay, so you can almost fill this in with intuition. I don't need anything here. Looks like I need a pi bond here. Looks like I need 2 more bonds, so I could do 2 pi bonds. Looks like I need another bond. I could do a pi bond here. This looks okay. Fill in the electrons. So you can almost do that by intuition, but we're going to do it systematically through this topic, and then you can use your intuition if you get better at that. 6 carbons, 24 electrons, 6 hydrogens, 6 electrons, 2 oxygens, 12, adds up to 42. So what do I got? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I got 26. 16 electrons left over. Now I have oxygens, so I'll put those on the oxygens first. 2, 4, 6, 8, 10. So I still have 6 electrons. Now I have to start putting them on the carbons. So these carbons look the most bare of the electrons. So I'm going to put 2 electrons here and 2 electrons here. And then skip this guy, put the other electrons over here. So now I could borrow these electrons here to make that pi bond. I could borrow these and borrow these to make 2 pi bonds. I could borrow these and make one pi bond right here. So then we would get a structure that looks like this. This, in fact, is the best resonance structure. But there's other ways we could have filled in the electrons. So I'm just using this structure to show that. I push these electrons in and push these electrons over to this oxygen. Okay, that could have happened up here if I borrowed these and left that the same. But here I'm working from this structure itself. So I push these in and push these over. And when I do that, I get formal charge. So now I would have a plus here and a minus here, but I have the same number of bonds in both structures. So that part's good. But because of the formal charge, this would not be as good a resonance structure as this, and that's why this is the best resonance structure. Now I could even bring the pi electrons over, which I could have done. I'm sorry, the pi electrons here, bring those over, and push these electrons back to the oxygen. That's another possibility. And I would have a plus on this carbon, okay, and a minus charge. Now, this is not going to be as good because I'm taking away a bond. Okay, and then I could bring these electrons over to fill in that gap, but that would leave a plus on this carbon, which I didn't show. So there's other resonance structures that are valid, but these aren't as good as the structure right here that has full octets and maximum bonds. And this is the best full octets and maximum bonds and no formal charge. So I'm going to draw the 3D structure of this. So I'd have to probably start at the carbon-carbon triple bond because that's linear. So I would put that into the plane. And then when I got over here, I'd do a dash and a wedge for this side of the sp2 carbon. And then over here, I'd do a dash and a wedge and connect to this carbon, and another dash and a wedge, and then draw this as a tetrahedron. So let's take a look. Okay, so you can see that I drew this oxygen and this oxygen as sp2, and that's because when I look at this structure here, I see 3 bonds. There's a second bond here that's a pi bond, so that's sp2. When I look at this, I see a pi bond, so that's sp2. Now you might have missed that if you didn't get this extra resonance structure from this guy. Okay, but anyway, here's our triple bond. I put that into the plane. And remember that I can do a dash and a wedge. And then this oxygen is also sp2. So notice this bond to the left is parallel to this bond to the right. And then this has to go back. So this would normally be a dash and a wedge, but since I drew this carbon first, it kind of looks like a dash. This one's ambiguous in the middle. Now I drew this guy first, so that's going to be a wedge coming out here. That's not ambiguous. And then this is sp2, so I'm going to, oops, I should have a wedge right here, which I left out. And then that's a straight line. And then notice how I draw the electrons. Okay, so the lone pairs in the 3D structures, I draw a little circle and put 2 dots in them so that you can convince me that it's actually a lone pair and not just random dots on the page. Okay, and then here's our triple bond. So notice 1 pi bond is in the plane and 1 pi bond is in and out of the plane. Okay, the one that's in the plane is going to be part of the resonance system. The one that's perpendicular will not be part of the resonance system. And then I come down here, this carbon is sp2, so my straight line is pointing to the right, so I'll have a dash and a wedge. Okay, and then this carbon is sp2, so I'll have a wedge and a straight line in the opposite direction. Now, since I drew this one second, I have a wedge coming out. So this is ambiguous. This could be either way. All right. So this is a bigger challenge. I do have a question on almost every single exam that requires you to draw 3D structures. So if you can get pretty good at this, you can get those points on first midterm, second midterm, and the final exam. Okay, so here's another condensed formula. So we would have to draw the connections, the sigma connections. You might give it a try, and then we'll, this one's a little harder because I have a minus charge that could be at more than one spot. So give it a try, and then I'll show this down here. So here's a connection of the atoms. Oxygen connected to the carbon, H connected to the carbon. That carbon's connected to the next carbon, which has an H. And then there's a C and a C, and then another C with 2 O's as we've seen before, so they're going to be separate from each other. And then one of those is connected to the CH3. So in this case, this is going to be an ester, looks like. And if we count up all the sigma bonds, it should come out to 26. And if we add up all these electrons up here, we get 48. So that should be 22 electrons left over. We'll go to the oxygens first. So I could put the electrons here. That's 6. Let me go ahead and show that. So there's 6, and then over here another 6, and then over here 4. So 6 and 6 and 4 would be 16 electrons. and we still have 6 electrons left. So as before, we could put the electrons into the blank carbons that have less than 8 electrons. These carbons only have 4 electrons, so I put 2 on each one, and 2 electrons here. And so then I fill in the guys that need more electrons. I fill in a pi bond here, 2 pi bonds here, and then I bring these electrons in to make a pi bond. I could have borrowed these, but then I would have formal charge. So I'm trying to draw the best structure that I can first. And so now you'll notice I have a minus charge on this oxygen, and that's a good place to put a minus charge because oxygen's more electronegative. Okay, so this would be a good structure right here. There's another structure with an O minus, so it's not the best, it's a tie for the best. Now, over here, as we did before, I could borrow this pair in and push up. The reason I want to do that is I want to see that this is sp2 hybridized. I wouldn't know that unless I drew this resonance structure and had the second bond here. Now I could come all the way back down here and push the electrons in between these two. That's going to make a carbon-oxygen double bond. That tells me that this is going to be sp2 hybridized. And then I could move these over and move these over and give these electrons back to the oxygen. So I could push all the way down, and then that would show me an additional atoms hybridization, this guy right here. So now to draw the 3D structure, I have to kind of consider all of these structures, and it will look something like this. So the structure that I drew is this first one right here. So I have an O minus here. Okay, and so it's sp2 trigonoplanar. So I have a straight line and dash and wedge. Now I didn't actually start here. I started at the triple bond, and then as before in the previous one, I extended out from that. Okay, so again, this is sp2 hybridized. Now, if I wanted to, I could push the electrons in and make the pi bond here, as I show here, and then that would put the minus charge all the way out on the other oxygen. That's going to be a good resonance structure too, because again, the O minus is the best place to put the minus charge. Okay, so might not see all this right at once, but you should practice drawing this. It's kind of like you're sketching an artist model or something, and so by sketching it out, kind of hide it. So if I go back, take it away, and then try and draw it, and then put it back, then you can try and learn where these little secrets are hidden. Okay, here's another one. Got lots of these examples, but as many as I have, there's an infinite number. Okay, so basically you have to learn the strategy. So here I have 2 hydrogens on the nitrogen, it looks like. Looks like that's connected to a CH, connected to a CH, again a triple bond. And then it looks like I have 2 OHs on this carbon, and somehow I have an overall plus charge. Turns out there's several ways to do that. Okay, I add up all the electrons, again there's 42, so let's take a look. So if I put in all the sigma bonds, it looks something like this. So now when I came down to the end, I had an OH and an OH, that's a little different. And then I had an NH2 on this end, that's a little different. So if I add up all the sigma electrons, that comes out to 26. I had 42, so again there's 16 electrons left over. So I'm going to go to the most electronegative atoms first. That'll be the oxygens. So I got 2, 4, 6, 8. Okay, and then the nitrogen, 10. So then I got 6 electrons still left. So I fill those in a manner similar to before. And then I started bringing them in to fill in carbons that are missing a full octet. So I'm going to make a pi bond here. I'm going to make a pi bond here, which I could also have done here, but that would make formal charge. So I'm doing the best way first. And then I could borrow both of these electrons to make a triple bond. Okay? So this would be our first structure. And you can see when I borrow these electrons, I have a little problem up here in that the oxygen has 3 bonds and a lone pair, so I'm going to have a positive formal charge on this oxygen. Now I could have borrowed these electrons, push these back and give them back to this guy, and then I would have the positive charge on this guy. These two are equivalent structures, and they're both good structures because I have maximum number of bonds and full octets. Now I do have the positive on the oxygen, which is more electronegative, but they're both oxygens, so there's no difference between them. But if I come way down to the other end where the nitrogen is, notice how I have pi bonds, sigma bond, pi bond, sigma bond. I could push in here and make a pi bond with the nitrogen, and then push all these electrons over to give that oxygen back its electrons, and it has no formal charge. So now the formal charge is on the nitrogen, but I still have the same number of bonds, and I have full octets. So now I'm comparing a nitrogen positive to these two with the oxygen being positive, and so I say it's better to have the nitrogen positive because it's less electronegative, okay? But that's only because they all have the same number of bonds and full octets. So this nitrogen is going to be sp2, this oxygen is going to be sp2, and this oxygen is going to be sp2. These guys are pretty clear in terms of what they are. So again, I would probably start with the triple bond first, and then this should be kind of familiar now. This is probably the third time we've done this. Again, this should be a wedge, which I forgot. But coming at it from this side, this is a straight line, and then I have a dash and a wedge. And that comes out to this carbon, which should have a dash and a wedge, but we drew the wedge first. So all we have is the wedge. Connected to the nitrogen, which is sp2, so dash and a wedge. So I could bring the electrons in from the nitrogen, push these over, push these over, push these over. Notice that's because all the p orbitals are parallel. They can all communicate the electron density to each other. And that would be the best resonance structure, which I have here, but I didn't actually draw that one. This structure that you see right here works for everything. Okay, we're not going to change any 3D atom here at all, just the p orbital electrons. Okay, so this is sort of like might be an exam question type problem. So again, I have a condensed formula, and from this you have to figure out how to fill in all the sigma bonds. I have some numbers here, 1, 2, 3, 4, 5, because I'm going to ask you questions about the hybridization and the bond angles and the shape and the number of sigma bonds and the number of pi bonds and the number of lone pairs for each of these atoms that I'm pointing to. So I have a CH3, and then a C, and a C, and then a CH, and so forth. Let's go down the line and take a look. There's a CH3, and I already filled in the triple bond. Then I have a CH and a C with a methyl. That's this guy right here. There's a double bond there. Then I'm going to have a C double bond O, and then that's all going to be connected to an NH. And then I'm going to have a CH2 and NH and CH3. So these are all sp3 hybridized. So that'll continue on down the line. So now I labeled the nitrogens differently. So I have an Na and an Nb, because I'm going to ask a question about that. What's the hybridization of Na? So when you look at that, you probably think sp3, because I don't see any pi bonds. But what you're not seeing is I can bring these electrons in to make a pi bond and give these electrons to the oxygen. That would give me a plus formal charge on the nitrogen and a minus formal charge on the oxygen. But it would show that the nitrogen has a double bond. Okay, so this is really sp2. Now this nitrogen I cannot bring over towards either direction because these are sp3 atoms. There are no p orbitals. Okay, there's nothing I can do. So this is going to be sp3. Okay, so this will be sp3, sp3, sp3. We'll make that zigzag shape that we talked about. Now, as far as the atom 1 right here, okay, that's connected to next to the methyl, that would be sp hybridized. And if it's sp hybridized, we'd have to say, well, that's linear, 180-degree bond angles. Now, as far as number of sigma bonds, we come up and we see there's a sigma bond on the left, there's a sigma bond on the right, so there's 2. As far as pi bonds, there's a second and third bond here, that's 2 pi bonds. And carbon just makes 4 bonds, doesn't have any lone pair in this particular structure. Okay, if we go to the next one, this carbon right here, that has the CH3, okay, this carbon, we can see that's sp2, trigonoplanar, and 120-degree bond angles. Number of sigma bonds will be 3, number of pi bonds will be 1, and there are no hydrogens. Okay, if I look at number 3, I guess that was number 3. So the one that I did before does have a hydrogen here. So the one that has the methyl on it, the CH3 here, does not have a hydrogen. Okay. So, I'm pointing at the methyl here. I'm sorry about that. So the methyl right here has no pi bonds. So that's going to be tetrahedral. It's going to have 4 sigma bonds, no pi bonds, no lone pairs. And then I'm coming down to the nitrogen. That would be Na right here. That's tricky. Okay, so Na, we have to recognize the resonance structure. So that's going to be sp2 trigonoplanar 120. In this particular structure that we're looking at, there's 3 sigma bonds. Okay, so we're not seeing the pi bond. So this one will have a different answer depending on which structure we use. But in this case, there's 3 sigma bonds. There's no pi bond, and there's 1 lone pair. And then the last one is the NB, this guy right here. And so that's going to be sp3, tetrahedral, 109, and there'll be 3 sigma bonds and 1 lone pair, no pi bonds. Okay, if I drew it out in 3 dimensions, it would look like this. So you might want to try and draw that yourself. See if you can get something that looks approximately like this picture. That's how you learn to draw them. Okay, so as you get better, you can draw these quicker because you recognize the key features and where you're making mistakes. This guy right here, again, is kind of the trickiest atom in the whole thing. That would be sp2, so that would look something like this. Okay. So I have, I think, one more here. I think that we're down to our last guy. And so I have a condensed line formula. We want to draw that as 2D. So I do it like that. I mentioned there's a 6-carbon ring. That's this guy right here. Okay, and then you could count up all the electrons, but I would just say it looks like a triple bond here. Looks like a lone pair here. Looks like I alternate pi bonds here, either side. Pi, single, pi, single, pi. And then I have a carbon group with R, carbon group with R. Looks like a double bond here. Both of these guys need 1 more bond. I think a double bond here, probably a couple lone pairs here. I can fill in all those details. You can try and count up all the atoms, but that's a lot of work. Take you a long time. Intuition works better here. Okay, so I filled in a possible pattern of the electrons. There's multiple patterns, multiple ways to do this. There's a lot of resonance structures here. Okay, so it would look something like this. This would be the best resonance structure because I have maximum bonds, full octets everywhere, and no formal charge. Okay. Now, if I tried to draw that out, places where you might get in trouble would be on this nitrogen, because you might draw that as sp3. But in fact, this lone pair can push into the pi bond. And so that's going to make this sp2. It's just hard to see right here. This looks pretty clear, sp, sp, so this is linear. I probably would start drawing this one first, and then continue into the ring. These are all trigonoplanar, so they'll have dashes and wedges, and a simple straight line. On the other side, I have a simple straight line. This is sp2, so probably a dash and a wedge. And then this is sp2, so simple straight line and a dash and a wedge. And then this is sp2, simple straight line and a dash and a wedge. So it would look something like this right here. Okay, that would be a nice job if you could draw all that out from this structure right here. And if you can't, then practice drawing this out, and then hide this structure. So you take it away, and then bring it back, and see if you can generate that. Now, when you look at this particular structure, I'm asking you here, which atom wants the electrons the most? And so you should come down and look at this oxygen and say, well, that's the most electronegative atom. That wants the electrons the most. Now, could I show that in a resonance structure? Well, I could. Because went the wrong way. Because I could add in these electrons, take them from being shared to give it to the oxygen. Now, carbon's not going to like that, because I took the electrons away, and I would have a plus charge. But there is a pi bond over here, so I could borrow these over, and then this guy would be happy, but now this guy's not. But I could borrow these guys over, and then this guy would be positive, but then I could borrow these guys over, but then this guy would be positive, and then I could borrow these guys over, and this guy would be positive, and then I have a lone pair here that could come in and satisfy that problem. So this would be the second best resonance structure if I did all of this, because now I would make, I would get this bond back, this pi bond. But because I have formal charge, plus on the nitrogen and minus on the oxygen, it would not be as good as this original structure. Okay. Here I did it all at once. So you have a choice here. The oxygen wants the electrons, so I could show that just the way we did on the previous slide. And then I have a minus and a plus, and I could start the electrons moving the way I did on the previous slide. But I also have a choice of starting here at the nitrogen, because the nitrogen can push its electrons into pi bonds. And ultimately, this would go all the way to the oxygen, so this is a good push right here, okay? Because nitrogen's more willing to lend its electrons than an oxygen. Okay, so you could start on either side to write these resonance structures. And so this particular resonance structure is the second best structure, because notice I have the same number of bonds and I have full octets. But the thing that makes it not as good is I have a minus charge on the oxygen and a plus on the nitrogen. So again, there's many resonance structures possible here, and you would certainly need to draw this one to show that the nitrogen is sp2. I think everything else is pretty evident from the original structure up here. And that brings us to the end of another topic, and hopefully this can help you draw those 2 and 3D resonance structures.